Today, we are going to talk of something called generative adversarial networks. This breakthrough came in 2014. It turns out that one of my relatives, actually a nephew, was on the paper. It's Ian Goodfellow and all these big guys, but it also has somebody I happen to know. So many people have hailed it. For example, Lee Kun has hailed it as probably the single biggest breakthrough in AI in many, many years. So, and it is being really talked about quite a bit. It led to many good things and many bad things. Amongst the good things we'll talk about, but amongst the bad things that it led to was deep fakes, which have become quite a nuisance these days. So they are an extremely powerful neural architecture. And this neural architecture is different from what you have been studying so far. The standard classifiers and regressors that you have been studying, it's quite different from that. And the best way to understand it is with a sort of a frame, to frame it as a game between two adversaries. All of us, at least, have played a cop and thief in our childhood. Right? So that is the best way to learn about these networks. So imagine that there is a generator of counterfeit money, right? And sort of there is a generator. So we'll call it a generator. This is your thief, generator, and it generates some counterfeit currency. You know, $1, whatever 10. Is there a $10 currency? Probably not. Like whatever the denominations are, $1,000, etc., of different years and different things like that, right? And there is a police whose job is to find out whether a bill that it receives is fake or correct. Discriminator. Discriminator's job, did I spell discriminator correctly? Maybe there's no I here, I forget. Discriminator. Its job, it's the police. Its job, now you know that this is the thief or counterfeiter. So this thief will always try, if you are in the business of creating counterfeit money, what will be your goal? To create as accurate a money as possible, you know, a dollar bill as possible, so that the police cannot catch it. And what is the goal of the police? They'll try to get pretty smart at it. They look for all sorts of subtle clues to be able to tell when a currency is real. So let's say that you have a pile of real money. Real money, right? So you have $1, $10, $100, $1,000, and of all different kinds of years. So as you know, the bills have many, many variations. Each of these bills go through lots of changes over there. So think of it like that. So what you do is, so the thing is, they have their adversaries, right? The generator or the thief will try to pawn off as much counterfeit currency as possible, right? Because that's how the thief is going to make money. The police will try to catch as many counterfeits as possible, isn't it? This frames the game. As many counter possible. So this is interesting. Now comes the very interesting part. So let us say that in the beginning, you have a blank slate. The thief doesn't know how to create good counterfeit money, and the police doesn't know how to recognize counterfeits. They are both novices. So now let's try to teach them. what you can do is you can ask the generator, the counterfeit, the thief, to produce some bills, right? So this will be fake data, right? Fake. And then you take a few real data, real currency, and images of them. And then what you do is you create a batch in which you sort of give half and half of this. And then what you do is the real currency you label as real. So now you create data to train the discriminator, to teach the policeman. You tell him that, see, look, this is real. This too is real. This too is real. And the other one is fake. This other one is fake, right? And so forth. Are we getting the sense of it? You can label the data. In other words, you are the expert. Let's say that you are omniscient. You can see what really is going on. And you can give this police some lessons to learn, right? A table, you can show these are reals and these are fake. So what will the police do? Let's say that it will, in the beginning, if you think of the police as just some neural net, a police neural net, it will have random weights, randomly initialized weights. So what it will do, and the last layer, you can make it your logistic unit, logistic regression. Why logistic regression, guys?
Classification.
Yes, all it is doing is real or fake. It is answering either 1 or 0. But more specifically, it is coming out with a probability of, let's say, real. I mean, we can take probability of fake. It doesn't matter. One way or the other, it's the probability of the real, right? So for the classifier, so discriminator is in a sense a classifier that tries to classify as well as possible. Are we together? Right? So do we remember the loss function for the classifier, guys?
ELP.
Softmax?
Yes. No, the loss function. The loss function, classifier loss
Cross
function.
entropy. Yeah,
Cross
BCD.
entropy.
Yes, very good. Classifier loss function. Amongst other things, a common one is cross entropy. Cross entropy loss. Right. So, for example, the loss would be, the summations and so forth. So, let me use the notation that is used in these papers. When I say when I write this E with this peculiar double bar, think of it as, in some sense, roughly the same as doing this 1 over number of data points of something, averaging it, finding the expectation. There's more to it, but let's just stick to this definition. So I'll use this big E. So this would be what? It would be the expectation of log of real. So when will it be 1? When you give it real data, right? Real data. P for data, let me call it data, right? Probability for the data. And then there would be, if you add one more to it, you will get a log of, by the way, if this E is getting a little bit fake, probability of fake. If you remember, this used to be the cross entropy thing. Let me write it out as minus this. If you remember, it used to be this, right? ln y hat, isn't it? Minus for a positive case, and y, right? For the negative case, again, y ln, of course, there's a I here, y ln, sorry, 1 minus y ln 1 minus y hat, right? So basically the converse of it, right? Roughly speaking, you don't write it in so many words. You tend to just symbolically write it as y ln yi, just to be brief, y hat. And sometimes when you know that this is a positive case, yi is the positive one, sometimes people brief it as this, and the other term as ln 1 minus y hat. when they know that it's the negative case. In this case, it's the fake. Right? This is the real. So this is a little bit of a mathematics that you may or may not remember from our earlier sessions, but take it as a fact that there is a cross entropy loss that you can use, a very vanilla garden variety cross entropy loss you can pick up from for a classifier, and that will serve the purpose for your police. Right? So let's go back to that image, and I'll redraw this image. So there is a thief. uh, Traditionally, the thief is represented like this. A thief. It is the generator, the thief, and this gets some input, but it tries to produce a fake, right? A good fake. And then this fake you feed into, and then you take a pile of real data, and then you sample from that. So now you get the training data for the discriminator, which is basically a classifier of sort. Is basically a classifier. Its job is to tell fake versus real. Right. So now comes an interesting thing. Do you see that these two, the thief and the police, they have adversarial relationship as in real life, right? The thief would like to pawn off as many counterfeits as possible. The police would like to make sure that most of the counterfeits are catched. Do we agree, guys?
Yes.
Something simple that I'm saying?
Yes, sir.
Yeah, it is, right? And so how do you train this? What you do is, let's follow a few steps, and I'm giving you the more non-mathematical sort of a way of looking at it. To train the discriminators, step one, you just make the generator in the beginning. The generator is not trained. The thief is a novice. The cop is a novice, right? You ask the thief to produce some counterfeits. He'll produce the most useless counterfeits, isn't it? It might not even have the denomination or something. It will just have some random image on it. So you produce a small batch of counterfeits. Let's say that you produce 10 counterfeits, and you take 10 real. It becomes your mini batch. Your mini batch becomes mini batch 10 real, 10 fake. Label data. You label it. Then you pass it to the cop. The cop is again completely untrained, is a novice. So what will it do? It will make the cop is going to make a lot of mistakes. It may randomly call a good dollar bill a bad one, a fake one, and it may randomly call a fake dollar bill as a real one. So in other words, the loss of the discriminator will be high. Are we together?
Asif, can I ask one question?
Yes.
How is the generating this fake images? Are we feeding it into the dimensions and the images, or?
Yes. So what you do is, and this is a very interesting thing, people use a mathematical language, but just imagine that you give it a random data, just random data, random numbers. The word that you use is, you can give it random Gaussian bell curve, or random normal, or random uniform distribution. What is uniform? Just between 0 and 1, pick a random number and just feed it in. So the only purpose of that input is because neural networks expect some input. So just throw in some random input. It doesn't really matter. And this is the beauty of this actually architecture. You'll realize that this input is an irrelevant thing. Are we together? Right. It has a mathematical relevance actually. It belongs to a class of algorithms which make beautiful use of randomness. Things like Metropolis algorithm, Hastings Metropolis, and so on and so forth. There are a lot of algorithms that significantly benefit, and they use randomness to their advantage. So we'll soon realize that it belongs to that class of algorithms when we go a little bit into the math of it. But today, let's get the intuition right, guys. Huh? So Prachi, are we clear? This is just something, it doesn't matter. You just feed in something random. Just think of that, it's just a trigger point. The generator now gets data and says, aha, I need to do something. right? And what it does is it somehow magically produces a fake.
So even the dimensions of the image don't matter, right?
That you can match. That should matter. So all of these images should be, let's take a number just to make it very real. Huh? 64 cross 64 cross 3. So make sure that your fake image is also 64 cross 64 cross 3.
Okay.
Are we together?
Yeah.
Right? So you try to, I mean, use basic common sense, you produce that. Now what will happen is this cop will make all sorts of silly mistakes, right? Randomly give some values. So when you compute, the measure of error is the loss in the discriminator. That will be high. So what do you do at that stage? What you do is, what can you do with the loss? Guys, how does a machine learn from the loss?
You go back and adjust the weights.
Yeah, so you go back and adjust the weights in the discriminator, not in the generator, in the discriminator, right? You go and smarten up the police. Then it is shown the real answer and it says, oh my God, I got it so wrong. So then it begins to see the differences between the fake and the real, the cop, and then begins to say, all right, I'll do a better job now, right? So the weights of the will get adjusted by this WD, some weight of the, think of that, and I'm just writing it as a giant weight vector, the giant weight matrix. So the weight matrix, all the weights of the discriminator, they will all improve. So what happens now? The next time it will do just slightly better, isn't it? Right? So if you don't train the generator anymore and the generator keeps creating really lousy fakes, and you just keep on training the discriminator, what will happen? Sooner or later, the discriminator will figure out how to very accurately distinguish between real and fake, right? For example, the real will actually look like a dollar bill, but this generator, which has not been trained, it is just printing garbage images on the paper, on the 64 by 64 by 3 images are just random noise, isn't it? So would you agree that if all you do is keep training the discriminator will keep getting better and better at recognizing real from fake? Right? So if the next step, I don't do anything to the generator, but I again make another 10 fake images from the generator, another mini batch from the real data, and I put it together and give it to the police, right? Once again to make prediction, then let the police see the mistakes, which is the loss, and then learn from those mistakes. What will happen? Guys, I want some feedback. Everybody is on mute and it's very hard because I can't see you. I'm not getting
Be
feedback.
improving.
Yeah. So tell me when it is hard, guys, because if you recently all said that the sessions are getting hard, I want you to not feel that it is hard. It's very simple. Would you agree that if you were in the loop in which you just kept on taking random images from the generator and you kept on training the police will become extraordinarily clever.
Mm-hmm.
Yep.
Yep. Over time, the discriminator will get smarter.
We'll get smarter. It's just like real life. Yeah? Then what happens? But what you do is you don't do it like that. What you do, because now all that the police has learned is to catch very like hopeless and novice counterfeit makers, isn't it? Just hopelessly incompetent thieves he'll be able to catch. That's not really good. So let's try to smarten up the thief now. Right? So what you do is after this guy, the police has learned something, you do this. Next time around, you play the interesting game. So this was step one, right? Where should I write it? Let me write it here. So you realize that was step one. The cop got a little bit smarter. Now you go to step two in the cycle. In the step two of the cycle, what you do is you freeze the police. You say, police, you can't learn anything. Right? So how do you do that in the language of neural networks? How do you make sure a neural network doesn't learn?
Stop updating the weights.
Exactly. You turn off autograd. You make sure that it does not learn. Backpropagation doesn't take place through the police. Right? Or its weights never get updated. So now what you do is you again generate, this time through the generator, you generate, let's say, a batch of images. I'll just say 10 images. or 20 or whatever it is. But then you don't take the data, no data. You only feed fakes, only feed the cop fakes. But when you feed it, deliberately you choose to misguide it. So you want to check how well the like from a thief's perspective, right? How will the thief know that it is succeeding? So what thieves do in real life also they will float some fakes and they'll pretend that it is real, isn't it? So let's do exactly that. We create label data for the police, discriminator and the generator. It will create, but every instance that you feed this time around into this, because it's label data, you say, you claim that it is actually real, right? Do you see that I'm putting 1 here? By 1 was supposed to be for real. The 2 was supposed to be for,
Fake?
oh, sorry, not 2. I apologize. 0 was supposed
Zero for fake.
0 for fake. But so what you do is you create data which deliberately is designed to fool the cop, because that's what you would do in real life. So you would give this 10, let's say 10 images of data, but you would claim that all of them are real, right? And so then what will happen? The police is not able to learn now. In this stage, the police will make predictions. What may happen is it may detect that all 10 are fakes. Like what will happen is you are forcing it to, you're saying that this is actually real. So let us say that the police has gotten a clue, right? Some little bit it has learned. So what will happen? What will happen to your loss function? Because you're misguiding it, the police will this time end up with another loss, mistakes, isn't it? In fact, the better the police is, the more the mistake it will make with these fakes. Are we together?
It's better, Asif. Why would it make a mistake?
See, suppose the police is perfect. He can tell the real from fake. So what will his Y hats be? So this is your X, this is your Y. What will his Y hats be? All of them will be close to 0.
0.
Right? 0.1, 0.01. They won't be close to 1. They'll be very, very small values, isn't it? So if the police is good, his predictions will be very small. Are we getting that, guys? So let us say that you have a pretty smart police. He will pretty much predict that all of these are fake. The probability that they are real is close to 0. So this is a crucial point, guys. Make sure you understand that. Do you get this? If the police is smart, he will say, well, he looks at a fake and says it's a fake, but you have given it label data claiming that that is not fake. So what will happen? There will be a big discrepancy between the label and the prediction.
So if I were to use the older terminology, you're using that model in an apply mode here. It's not in a learn mode, right? You're using the discriminator in an apply mode.
Exactly. The discriminator, the police is just applying the learning, or it is just in inference mode or predict mode, inference or predict mode. It is just predicting. It's not learning anything. Whatever it has learned in the past in step 1 is fine, but now it is making prediction. And you know, the cop may have picked up a lot. It might have picked up a little, right? But in any case, because you're deliberately trying to fool the police with your data, what will happen? Its predictions will be hopefully different from your labels. The Y hats will be different from Y. Is it making sense to anyone, guys?
Yes, Asif.
Yes.
Right? It's simple thing, right? So if it is there, so what will happen is you'll end up with a loss now. Let me call this the loss with respect to the generator. Now, what you can do is you want to adjust the weights in such a way that this loss decreases. Why? Because you want your counterfeit, the cop to predict what would you want it to have do. This is the police's prediction. Whereas what the thief wishes, what does the thief wish? The thief would wish that the numbers are closer to 1, 0.951 or something like that. This is the thief's wish, and this is the police's prediction. If you notice between this, the loss is big in the beginning, whereas when the thief reaches the thief nirvana or the thief heaven, all his counterfeit will go through, and the loss in that time will be low. Does that make sense?
Yes.
It's as simple as that. So what do you want to do? The thief now goes and says, hey, let me do a gradient descent of the weights with respect to the thief. So instead of saying weight with respect to the thieves, I'll just say gradient descent with respect to the thief of the loss, right? And so you say that this network has updated itself. So see, that technically I should say some weight in the thief has now gone to weight. The weight matrix has gone to weight minus alpha W. This is the strict thing, the G. But I'll just sort of a cheat because it's a lot of notation. I'll just say that the generated model somehow has updated itself. The thief has become a little bit smarter, right, in the second step. So what happened in the first step, the cop got smarter. In the second step, the thief got smarter.
Asif, in this case, the only nuance I'm observing there is you only get one kind of errors, right? In the training mode.
Yes. Yeah, there's only one error. No?
Yeah.
See, it's a binary classification. A currency is either fake or it is genuine. It's counterfeit or real.
Now, what I meant by the one kind of errors is the only errors that will be fed back to G is cases where a fake was detected as a fake, right? But it doesn't give.
But it is not producing fakes. See what happens, it always G will never not produce a fake. G will always produce a fake. That's it.
Okay, yeah, okay.
You notice that the thieves don't have the US Mint, right? Money-making printing press. So obviously counterfeiters can only produce counterfeits.
Okay. In that case, it's the universe set for it.
Yes, exactly. So what happens is that, so guys, follow me. I'll just repeat what I said. In the first step, what you do is you give to the police a bunch of real and a bunch of fakes. And then you say, okay, go make the classification. So it will make mistakes. If the cop is a novice, he'll make mistakes. So then you back propagate his or her mistakes, and then you update the discriminator. You update the cop's intelligence. It's become a little bit smarter. It's learned something. But then now the thief is in trouble. The thief is losing. So what you need to do, you need to make the thief a little bit smarter, which is what they do. So the next time around, you don't let the police learn. In the second step, you let the thief get a little bit smarter. And so what you do is the thief, of course, publishes all its data. But this time when you are training it, you deliberately misinform the police. You tell that what is coming from the thief, the fake currencies, are actually legitimate, because you need that. You need the loss function from that to back propagate and do that. See, because when will the thief be able to learn? When it gives to the police saying this is real, and the police says that no, the probability that it is real is 0.1 or 0.01. Then the thief says, oh God, we are screwed. We better go find what is the obvious thing we missed on the currency, isn't it? Maybe they forgot to put one of the founding fathers or whatever, Washington, on top of the currency, right? Massive blunder. So the way they would learn is they need to get trained themselves, right? So see how much you can fool the cop. So you can't fool the cop much, it means that you need to back propagate this thing, and all of those gradients back propagate and come back to the thief. And here is the beautiful thing. How is the gradient back propagating? And this is sort of the diabolically fun stuff. So you realize that the predictions are always being made at this level by the police, right? So the loss function is always with respect to the police's predictions, right? So actually what happens is that the gradient flows like this, except that here you won't, the police will not update the weights, her weights, and the counterfeiter will get to update the weights, will learn something from it. It is, there's a very intuitive idea. What the counterfeiter does, imagine that they are listening to the gossip of the policeman, right? And they're sort of keeping their ears to the ground and asking, okay, what is the cop able to figure out? So let's say that the cop has figured out that the digits are too small, right? If that's the feature the cop has learned, because the gradients are flowing back, it is almost like, the thief is listening to it. Do you see that? And then it says, okay, let me make it a little bit smaller, right?
Asif,
So, yes.
um, since we discussed the backpropagation as the part of the chain rule, does
Yes.
this mean you take the whole model of the discriminator as just one step? So we don't anymore, because we're not
Keeping the
changing.
discriminator as a black box. Just think of it as a simple classifier. If it helps your imagination, just think of it as just a simple logistic classifier, one node.
Okay, and since we froze that node, we don't. So when you do the chain rule, there's no loss at that point, right? The loss is after.
No. Loss has nothing to do with the upgrades, no, Patrick. Loss is the difference between prediction and reality. Y and Y hat. Remember. So when you freeze the cop, the cop goes into just the inference mode. It doesn't learn anymore. She doesn't learn anymore. So whatever data you give, the learning that she has acquired till then, she will use that to make a prediction. And in the prediction, there would be a certain amount of errors, which will be quantified by your loss.
Oh, I understand that part, Asif. I was just wondering how the backpropagation starts from the loss generated by
Yes.
the
Oh, this is your chain rule. This is your standard chain rule, backprop. See, okay, let me just mention the 4 stages. We did that in code, right? Let me remind you of the Python code. First, what you did is you took the network, which had the forward method. Given the input, it would do the forward computation, right? So what was the PyTorch code? You would do network X. This is invoking the forward. What is it producing for you? Y hat, isn't it? So you would take the actual Y, the actual X, and now you feed this in. So now out comes Y hat. So now you know X, Y, Y hat, 3 things. So this is step 1. What is the very next thing you do? You compute the loss. Loss is equal to whatever your loss function is, right? Let's say cross entropy, and you give it Y hat. Do you remember this was the second line of your code in the inner loop of learning? And the third line of your code was, now that you have the loss, what do? You do backwards, right? You do network backward. What does this step do? So this is step number 2. What does this do? It computes. Let me just write it in another color. Computes and backpropagates all the gradients. But see, just because every layer now has the gradients does not mean that it will actually do the step 4. Step 4 being gradient descent, which is W is equal to, in simple form, W minus alpha W. See, any given weight needs to do this, right? To learn. This is the learning. This is the real learning part. Learning step. Do we remember, guys? Patrick, do you remember that this is a core loop? Literally, we see it as 4 lines in the PyTorch code.
Yes, Asif. So I'm imagining in the
No.
part
No, hold on. So hold on. So now, suppose I don't do this, I don't allow this learning. Then what happens? For the police, I prevent this learning from happening. So it will compute the gradients. It's all right. The gradients will get will get computed. Let me redraw this image. Here is a thief generator. Here is real data source. So at this particular moment, here is the police, the discriminator. So you end up with a loss. Loss will cause the gradients. The loss, once you compute, then the gradients will go all the way back to the source, right? Because here is a random, actually this source, for historic reasons, people always write it as Z, random data of some sort. But it doesn't matter. What is interesting is that this doesn't matter. What matters is that if the back propagation flows through this, you don't allow the thief to learn, but you can allow you don't allow the police to learn, but you can allow the thief to learn in the second step, isn't it? So what will happen in step one, the cop learns. In step two, cop learns. Step two, thief learns. Are we together? Where this is the thief, generator is the thief, and this is the cop. Patrick, is this making sense now?
Yes, Asif. So basically here, it was step four. Step four had like a gated process where the first part was you didn't allow the other one, the generator, to update, but you just let the discriminator. And then the second step, you allowed the discriminator not to update, and then just the generator.
Yeah, because I use the word steps here, let me just call it cycle one, cycle two. So one cycle of data, one iteration number one. So you alternate between iteration. The iteration one would be, take a mix, take a 50-50% mix, a 50% mix of real and fake currencies, images, label them correctly. How can I label them correctly? Because I am taking data that's coming from here, I can label 1. Data that's coming from the generator, I can label 0, right? Label them correctly. Let the cop predict. Compute loss, backprop only to cop. Let the cop get smarter. Let the cop learn. Are we together, guys? Then in the second, and this is the alternating step you do. You alternate between this and this. The second step is, can somebody remind me what the second step is? What do we do this time?
You freeze the learning of the police and let the thief learn.
Yeah, exactly. Freeze the cop's learning. So the cop cannot learn. Then feed it deliberately misguided data. So this is the time for the thief to get smarted. So the thief will now pawn off a counterfeit currency as right ones and deliberately feed counterfeit, fake data to cop, but claim, label it as real. Because this time it is the thief who's trying to figure out how much will the cop actually catch if I try to pawn it off as real, right? Then take the loss and backprop and update or gradient descent the thief, right? Are we together, guys? So what will happen is in one step, the cop will learn. Then the next step, the thief will get a little bit better. Then the cop will get a little bit better. And then you repeat the iterations. You keep on cycling between this. And the amazing thing is that, see, you have a large corpus of data, actual data. So you're sampling into it and picking up a mini batch. But as far as the thief is concerned, As with counterfeit money, you have a random generator. You just need a trigger, and the thief will just go and just freely generate as many images as you want. Right? There is no effort. There is no data constraint. It's a generative. That's why you use the word. It's a generative model. It will go and generate it, right? As many fakes as you want. And so little bit by little bit, do you see that they keep making progress? What will happen in in this peculiar cat and mouse game between the thief and the cop? What do you think will happen after some time? Can you guess?
Both get smart.
Both get smart. They both become very smart. And in fact, this is a classic game theoretic problem. Those of you who took AI and with course may remember, and if you don't, most of you have not taken AI course because in our generation, I suppose it wasn't very popular. So this is a name for that in AI. We have and game theory, we have a name for this sort of a thing. It is called minimax. So we'll introduce maybe the math later on in the second half. So this is called the minimax algo. So what does it mean? The thief, the cop is trying to minimize the mistakes, and the thief is trying to maximize the mistakes that the cop makes. Do you see that the goals are opposite? It's a two-player game, and it's an adversarial game between the cop and the police. Right? Now, whenever you play an adversarial game or things like that, in game theory, there is a concept of a Nash equilibria or Nash equilibrium, right? So what it means is that, imagine, and at this moment I'll make hand-waving arguments. Later on, I'll make it more precise. Yeah. So imagine that in some space, right? It's somewhat like, descending to an optimal solution. So there are certain points of equilibrium. And what will happen is this situation will roam around and finally hit upon an equilibrium. Think of it as some sort of a minima in the game, right? These points are called Nash equilibria. Nash equilibrium points. Right? And it's a sort of in the state space. So the interesting thing, by the way, Nash was a great mathematician who single-handedly created a whole revolution in game theory and in economics. So there was a movie made on his life, which if you get a chance, see it. It was called
The Beautiful Mind, right?
Exactly, Beautiful Mind. Beautiful Mind movie, and in fact, much better than the movie. I always found, actually, I found the movie, good as it was, to be almost, well, nowhere close to the actual book. The book is far superior, called The Beautiful Mind. It's on the life of Nash. So anyway, if you get a chance, you might want to watch the movie at least. So that is a minimax. And this is applicable here. It says that you'll ultimately reach one of the equilibrium points. So this sounds very good. We'll be able to solve this. This was the initial idea proposed in the paper, Generative, Adversarial Networks, right, by all of these authors. This is 2014. It was a game changer, guys. It was to computer vision in those days, a massive, massive game changer. Why is that a game changer? Because think about it. If the thief becomes really good at counterfeit, right? The thief becomes very useful. You can forever go on printing new money, right? Or in a more practical sense, now the thief can generate the kind of data that you want. It becomes a generator of fake images and fake videos. Do you see that, guys? It can perfectly well create a scene that doesn't exist. And the discriminator, the cop, won't be able to know the difference.
Asit,
Yes?
can you give me a couple of examples where this can be applied?
Yeah, I'll give the examples. In fact, I'll bring up the paper itself, the generative adversarial network. Why not? Why do I not do it right away? But see, there's a little bit of a theory. If you just allow me, I will take another few minutes to explain the theory completely, and then we'll see examples. The examples are absolutely stunning. Right? It was a game changer in artificial intelligence. Many people say that really artificial intelligence actually begin to feel intelligent or something about intelligence with this GANs coming about. They're truer in somehow to the spirit of AI. Right? So hold that thought in your mind. Go ahead. Next question.
Asif, there was one question about if you scroll back to where you had the G and the D diagram.
G and the D diagram. Okay, there it is.
Yeah. Where were those two boxes?
Yeah, here are the two boxes.
Yeah. So now, okay, let's leave there. So in the explanation, when we were looking at optimizing, there was cycle one, you were essentially making D smarter, right? So that was one. That was understood. There's a backdrop algorithm, and essentially you did the gradient descent to get D smarter. The cycle two, why do we need to do backprop through D? Why wouldn't just the error be passed to G?
See, the trouble is, the trouble in this particular loss function is, the loss function is defined in terms of the weights here. It's just a mathematical reality. If you think of for example, if you think of a logistic, just think of a basic logistic unit. This is the output. Suppose this is your police, D, police, right? The simplest police you can think of is just a logistic unit. This is producing Y hat. You're comparing Y hat to Y to produce the loss. But this loss will respond to the changes of this guy, isn't it? You can compute the loss knowing the fact that, let's say you use sigmoid. You know how to compute mathematically the gradient with respect to the weights here. You have no way of computing the gradient with respect to the weights in G itself directly.
Okay, so you have to go through this to get to there.
That's right. And you know, there's an interesting bit to it, because what happens is that, in some sense, if you think about it, it is almost it's quite a diabolical scheme. These counterfeiters, right? They pass forward some fake bills. Then they look at the cops. If the cops pick it, identify it. So imagine imagine them sitting there with their donuts and talking about it, how smartly they caught the counterfeit bills, right? So these thieves are listening to it, and they know, oh, maybe the mistake we are making is the 2 is too big. I'm just sort of making it be sort of a real. It's never like that. The mathematics is more abstract. But if I were to caricature it a little bit, it would be like, maybe the digits that I put were too big, or the color was off. Okay, so what do I need to do now? I need to just go fix that, right? So that is what is happening, because when it flows back through the cop, you're listening to the chatter.
Okay.
So it's a very clever way of doing things. The idea itself is very elegant and clever. And that's why it was heralded as one of the biggest breakthroughs of this, practically of this century in AI in many ways. Many people said this really remarkable, and it's a game changer and so forth. Certainly it was considered for a long time to be the single biggest breakthrough of the since 2010. Right? And now transformers have come in, you see, in the world of NLP. So these are the two big ideas. The transformer I've already taught you, and this. So now the biggest problem that happens is, how do you know that this sort of games converge, that they actually come to a good solution? Because, you know, if the cop is stupid and the thief is stupid and they're having a hard time learning, this game can go on forever and it may never converge. You see the problem there, right? But thanks to the game theory and the Minimax algorithm, we know that it converges, right? And it converges to one of the Nash equilibria points. So then generative networks people began to design and do things till they hit a bit of a bad news. The bad news they hit upon is this. So imagine that you have, I'll just take an example. Let's say that there is a data set called Fashion MNIST. right? And there is a data set called MNEST. MNEST is a digit recognition. So suppose you have 0, 1, 2, all the way to 9, and human beings have written. So somebody will write 0 like this, somebody will write 1 like this, somebody will write 2 like this. And so, there'll be many, many ways to write this. So MNEST data set contains 60K images of digits, right? They are monochrome, they are 28 by 28, right? And then the fashion MNEST was created because MNEST became too easy for the modern neural networks to solve. For years, MNEST was a benchmark and very hard to make progress on. And then suddenly this came CNNs and deep CNNs, and there was a lot of progress. In fact, the year in which all of these things started getting trivialized and other ImageNet data sets and these things began to trivialize was 2014. The 2014 was also the year independently the generative adversarial networks come in. So here you have a shoe, let us say. You have a shirt or skirt, let's say. You have a shirt, let's say. You have a pant, let's say. So what it contains is labeled images of clothes, or maybe, garments and fashion items. Right? Deliberately to make it a little bit tougher because MNEST became too small. So now there is a problem with this game, with the adversarial network. See, what happens is that if you want the generator to be really smart, it should be able to produce each of these items. So if you think MNEST, it should be able to produce very good zeros, 1, 2, 3, all the way to 9, all the 10 digits, and fool the cop, isn't it? But the instability that comes in the system is that what it will do is it will produce a 1, something like a 1, slightly like a 1. And then it will check, did the cop catch it? Suppose the cop catches it, it will backprop, and now this time it will produce a better 1 and better 1 and better 1. And so what happens is that of all the 9 of the 10 digits, it will get fixated on 1. And so both the police and the thief and the counterfeit maker and the cop, they will both become very good in playing the game with 1, right? The trouble is the counterfeiter is not generating any other digits at all. It's just generating 1. So it hasn't learned to generate all 10 digits. You see the problem there, right? And so it gets stuck. So after a little while, what happens is that it becomes very good with 1. Then you get it unstuck out of 1, right? Because the cop has become too good. Then this will go and it will go to 2. It will start producing 2, right? Because now the cop has caught up. And then it will produce 3. So in other words, maybe it will produce 8, it will produce 5. It will keep cycling. And they will forever keep cycling back and forth, never stopping. Because either the cop and the thief will become very good with only 1 digit rather than all the digits, right? So that is a problem that these adversarial networks face. And so that the original one had this problem. And so there was a tremendous amount of research. And today GAN is a whole world in itself, just as transformers and NLP are a complete world in themselves. In the same way, the GANs, the generative adversarial networks, they're a complete world of research. And there is a tremendous amount of research in creating all sorts of GANs. There is one particular GAN I'll talk about. It is called DC GAN. Now, I can't talk about all of the GANs. They're beautiful things. There is cyclic GAN, there is this GAN, that GAN, and whatnot. We will actually deal with many kinds of GANs when we come to the image processing aspect of the second and the third part, right, of this workshop. But at this moment, suffices to say that we get the big picture idea. Right? And towards the very end, if those of you who are, actually, let me not do it today. See, I want to keep it at the level that it is easy to understand, but the minimax theorem, the way it maximizes is very simple. You use something called a symmetric KL divergence and so forth. The arguments, if you're familiar with mathematics, is like 4 or 5 lines of derivation, but I won't go through that. I'll keep it for the weekend. Why don't we do this? This weekend we will cover the GAN's original paper. Does that interest you guys?
Yes.
Yeah.
Yes.
So then we'll cover the mathematics there, huh? Because at this moment it may derail our discussion. I want to take you guys pretty further along this. So that's one problem. So then people have come up with various architectures to prevent it from getting fixated. One of the architectures that people have created, which is extremely successful, I mean, actually not actually, but for some time was very successful, was DC GAN, the next sort of a evolution for that. It stands for Deep Convolutional GAN, right? And this word is, I'll explain what it does. So what it does is, to the classifier is, roughly speaking, with minor variations, it is basically a standard CNN, right? So how does a CNN go? Wide, then lesser, then, it becomes bigger, smaller, smaller, but more number of items, right? And then finally you have the feed forward layers, right? The dense layer. And then finally you have a softmax. Do we remember, guys, the CNN, the standard CNN architecture?
Yes.
So this classifier is your discriminator. This is the police, right? And it will produce the y hat, and therefore you already know y, it will produce the y hat, and therefore you can compute the loss and y hat, and you know how to therefore train the police. That was easy. What you do for the for the thief is something that is most remarkable. You create another CNN, but you turn it upside down. You turn it backwards. So you remember that, suppose you start with big image, 128 by 128, 128 typically, across 3 channels, RGB channel, right? And by the time you go to the last conv layer, it has probably become like 4 times, and the number of channels has exploded. Maybe the number of channels has become 512, isn't it? So the image size reduces, the feature size reduces, the number of features increases, the channels increase. This is a typical CNN. Do you remember that, guys?
Yes.
Yeah.
Yes.
But actually, so what you do is you do something counterintuitive. You do just the opposite of that. For the thief, for the generator, what you do is, and again, there is a random, and by the way, this doesn't matter. It could be uniform random number generator, Gaussian random number generator, and so forth. Ignore that part. What you do is just the opposite. You create, for example, you may create a vector of random numbers of just size 100. So it is your Z is basically of size 100, right? And what you do is right here, you explode it into a deeper, rather deep, let's say 512, this is 100, let's say, or something like that. You create it into what would be like this. This begins to look like this, right? And then as you come closer to closer, it produces an image. So suppose this image was 128 by 128 by 3. The last conv layer actually is producing this image, which is 128 cross 128 cross 3. So now you see why it makes sense, right? You took some signal and you sort of deformed it into this image. And this becomes your, typically you call it X, is the generated function of Z. This is the input from the thief. This is what the counterfeit. Why am I forgetting the spelling of counterfeit? Is it F-E-I-T, I hope? Counterfeit? Anybody would like to correct? Counterfeit, right? So this is the counterfeit image that you produce. And it sort of makes sense because what do you want? You want to ultimately produce the image. And so your entire convnet is run backwards. The only important thing is, do you notice that there are no dense layers? Like after this, there is no dense layer because you don't, what you have gotten back is the original image. And at this end, you don't layer anything in the dense layer. A typical conv has convolutions followed by dense layers, flattening and dense. And as softmax, you don't keep all of that. You just keep this. Now, there are minor details. So, for example, you turn off pooling. There is no pooling here. Pooling. You turn off the stride. When you hop across, you have, instead of pooling, you do strides of 2. If you remember, pooling is stride of 2 typically if you use a 2x2 filter, right? But you leave the stride part, but you don't do the max or the average or any of these, right? And so you run this entire CNN. Some people also call it deconv because it seems to be the opposite of convolution in some sense, in their mind. So what you do is, if you think about it, what you have done is, suppose you have a unit line 0 to 1. You're generating numbers from this. And let's say that the picture is made up of pixels, which are all localized like this. So what it is doing is, in the 0 to 1 interval, it is localized like this. What it is doing is, it is showing everything to this, pinching everything to this. In many sense. Anyway, this is, I don't want to go into the math because now you'll say, how is this working? We'll do that over the weekend. But basically, it's a very interesting idea. When the generator network trains, it figures out what should it look like? What should the image look like, right? So I will give you a small intuition before the break. So imagine that the only thing you want to do, there is an image. That image is very simple. In the weight scale from 0 to 1 weight, ducks are here, right? And your elephants are here. Are we together? So, or your cows are here. Cow, duck. So a one-dimensional duck looks like this. Let's say duck. And a one-dimensional cow, let us say, looks like this or something like this, right? Maybe I'll make it wider because the weight of the cow is a little bit distributed and the weight of the duck is also distributed. Let's say that this is your weight scale on a scale of 0 to 1. Would you agree that this is a typical duck will look like this and a typical cow, the data of the cow will look like this?
Correct.
Right. So for example, one particular cow, one particular duck may be sitting here. One particular cow may be sitting here. This point may represent a cow. But a cow won't be sitting here. That wouldn't make sense. One instance of cow will not be with a value here. So, so what happens is that, imagine that the generator in the beginning produces generator. Let us say that it's only trying to get a sense of the duck. So it produces, generator produces a duck like this, somewhere in the middle, right? So now the duck should be, where is it? The duck should be here. So between the police has learned to look for duck weights like this, but the counterfeiter has produced this. Do you see the gap? This is in effect a measure of the loss, isn't it? Loss is related to this gap. It's a function of this gap. So in the learning step, when the generator learns, the next time what will it do? It will try to produce the duck a little bit, it will try to produce the duck a little bit here. And it will keep on moving like this. Does it make sense? It will gradually make smaller and smaller, lighter and lighter ducks. It won't make a duck of 200 pounds. Are we getting that?
Yes.
And now let's generalize this idea. And for cows, it will either produce this, right? It will learn to produce cows here. Because if you really think about it, so now let's look at the cow and duck in one dimension. Suppose you're, so this is it. This is your duck. This is your cow. In the beginning, you have a uniform spread of values, a uniform random number generator, uniform in the interval 0 to 1. It will produce values equally everywhere with equal probability, isn't it? It has a uniform probability. But what you really want is most of the time, you should successfully generate data here. So what you should do is you should basically have somehow change the shape of this uniform, if I may say so. So something like this. All of this will converge here, or something like this. Half all of this will converge here, and all of this will converge here. Right? You're changing the shape of this uniform distribution. You're bending the line basically to this. That's a distribution line. And that is what the generator learns to produce this function. Right? Now, if you were to look at it in 2 dimensions, so suppose what happens is that you look at the weight and size of the cow, right? So let's say that these are your ducks. The ducks are, so let's say that this is the weight axis, this is the size axis. Here are your ducks, light and small, and here are your cows. Right? And let me use green to signify predictions. You know, the generator in the beginning produces things like this. You see that, right? So if it produces things like that, even a rather dim-witted cop will probably succeed at, or quickly learn to detect counterfeit cows and ducks. Are we making sense? But gradually, what will happen is this uniform distribution will change to, after some time, you will notice that what has happened is that after some time, it has become like this. Guys, please mute yourself. So the points that this is generating is the generator will start producing points only in these 2 regions, because it knows that if it produces points most real images and everywhere else is a counterfeit, it will get caught. Right? So this is the journey. This is the learning journey for G, right? For the G, thief. Does it make sense, guys? So instead of producing green points all over the place, it will start producing green points in those 2 areas where it has figured out that it means something. That's where the real data is sitting, isn't it? And so once it is doing this, what has it done? You take this generator, and you ask it to produce something. It will either produce a good cow or fairly good duck. And you know, the amazing thing is that now you can produce images, countless images of cows and ducks, things that may not even exist. Guys, please mute yourself. Okay, please mute yourself.
Mute everybody. Asif, can you please mute everybody?
Okay, guys. So are we getting the point, guys? What happens is that, think of it from the point of view of a thief, and this is how thieves become smarter and smarter, right? And cops become smarter and smarter. So today also, I mean, in real life also, cops and thieves have a pretty interesting game going. Adversarial game going. And that is generative adversarial networks. And the amazing thing is, for the DC GAN, you have you remember, it gives you one thing that is really amazing. So DC GAN, what was DC GAN? The convolutional, deep convolutional. Right? Remember, the summary of that was generator, thief, look like a neural net run backwards, a convolution net run backwards, right, from a generator. And this was the thief, and the discriminator was a bona fide convolutional network, right, to finally a softmax.
The police.
This was the police, yeah, the police. This was the DC gap. And now what happens is that the internal representation they create, like for example, if you look at these vectors that they produce, the representation of the cow and the duck in the images, they have a property which is very similar to word embedding. So let me explain. Remember that word embedding, and we learned about word to vec, the word to vec. Do we remember these words, guys? We did word to vec. I talked about glove, but didn't cover it. Anybody remembers word to vec, guys?
Yes, sir.
Yes, we do.
Yeah.
So what was the point? You could do things like king minus man plus woman was queen, isn't it? Now the interesting thing is the same thing you can do with sort of a image latent, the people call it the latent space embedding, the hidden state of that, embedding of images. This is one of the lovely byproducts of DC GAN. So what you can do is, you have a picture of a man with glasses. I suppose this is a man with glasses, right? And then you take man with glasses, and then you do this. You subtract minus man. You take a picture of a man minus just a man. You take any picture of a representation of a man, average representation of man, right? So the man is like, let's say, something like this. And then what you do is you add some picture of a woman. So how does a woman would look? Right? So as you can see, I'm very good with art, right? I'm kidding.
It's abstract.
Yes. So you know what it will produce? Can you guess what it will produce?
A woman wearing glasses.
Exactly, and it will produce a very, fairly realistic picture that would fool most of us of a woman wearing now glasses.
So as if the question here is in this, given that this is a machine doing it, right? So
Right.
it would essentially be the guy, the man with glasses, his facial features would now show up with feminine features, but still wearing glasses, correct?
Yeah, what will happen is, typically what happens is, this person looks very feminine. Yeah, woman dominates, and the glasses come through because you subtracted the average faces of men.
Okay.
That's it. It's quite realistic. So let us do one thing. It's going to be 8:20. It's almost a break time. I want to make sure that you guys understood this.
Oh.
Let me pick some names. Pradeep, did you understand what I was explaining?
Yes, I did understand. The only parts are in the DC GAN, the first generator part, which is inverted
CNN.
CNN. That part I having little difficulty following that. What is the advantage of having the inverted CNN?
See, what happens is that you need to take some noise that's pretending to be features and deform it into an image.
I see.
That is all. Stick in there. Hannah, how about you? You've been very quiet. Are you getting it?
Yeah, partially. I probably need to listen again.
Okay. So what I would like to do, guys, is in the second half, I'll review what we learned once again. But before that, I want to tell you some other magical things that it can do. So one of the things you use a neural style transfer, there's something called neural style transfer. And you often use, one of the ways that you can do this is with GANs. So how do you do that? What it does is you take, it's called domain change. It's very, very effective. So let's say that you have a picture. This is a picture of you, of your baby, right? Your child sitting there. In my case, I have lots of pictures of my young daughters when they were young. When they were little children. Now they are young, but they are college age. So let's say that there's a picture of playing the piano. Right? So you're playing this piano or something like this. Now, this picture is a photograph. What you can do is you can take an artist, let's say you can take Rembrandt, right? And Rembrandt used to paint people, human faces and human with great feeling and evocation. So very evocative pictures. And he was a great master painter. Well, it so turns out that since he's dead, we can't have him come and paint our daughter playing the piano. So what you can do is you can feed it into this sort of a GAN system, and what you will get is a very realistic Rembrandt painting of your daughter, of the girl playing the piano.
Like the Deep Art website.
What's that?
You have in the portal, like the Playing with the Deep Art website, right?
Right, yes. Yeah. So this is it, guys. So it's very amazing. You can take a landscape and you can have Van Gogh repaint it for you in a beautiful painting. And it also leads to some very interesting style transfer. Is not just for images. You can do style transfer now for authors and language. You write a paragraph of text, and then your teacher, let us say, is somewhat unimpressed with the elocution in your text. You can immediately invoke any writer of your choice and try to do a neural style transfer of that writing style into what you have written, and you'll be quite surprised how effective sometimes these things can be. So this is the power of generative adversarial networks. And in the second half, we'll do some examples, and then we'll move on to the graph neural networks. This week, actually, I would like to do some labs on GANs so that it all becomes very real. You know, when you play with it and actually see it happen, it becomes very real. Now, the reality is, guys, that GANs, they are generative models. They feel like magic. How can you feed random nonsense into the generator, but nonetheless, the generator just deforms it into, you know, it will always draw a vector that is either here or it is here, and it will not do this. And the point is that those random input is just seed, it's just randomly making it pick from here or from here, draw a vector in one of these two regions of the feature space. That is where, for example, a cow and a duck are sitting. You know, the images of cows and ducks are sitting. And so it is also making images that don't exist, for example. Right? And not only that, it leads to additivity of images. You can do arithmetics. For example, you can take, you can now do amazing things, like you can say, can I have a table with an apple, right? And of all things, let us say a rocket on it, or a launch pad or something like that on it. And it will create it for you. Amazingly, it will do that. The other application, which is very interesting, is, and this is where natural language processing meets this images, you feed in text, you feed in a narrative into this GAN, where I'm putting the generator and everything together. You say a room with a window and a girl playing piano. And guess what the GAN will do? It will quite literally produce a person playing the piano. Right? This is as good as I can make it. And there is a window there in the room. And this will look like a pretty realistic room to you. Well, this one doesn't look realistic, but GANs are a little bit smarter than me at making pictures. And so just think about it, the potential for it. Or for example, just think of the potential nowadays for saying things like, You know, people used to do a lot of 3D modeling. People would say, here is my landscape. Can you see how it will look if I put a swimming pool here, if I put a few trees there and this and that, right? Now the potential is, and I'm sure that somebody will start commercializing these ideas and do this. There must be a lot of the commercializations already. Things move so fast. You just describe the scene. You just describe how you want it to look. And soon enough, it will produce a photorealistic picture of how your backyard can look, right? And it will not generate one, it will generate as many as you want. Each of them will be different, right? And it will serve the purpose for you. So that is the power of GANs. And as you can imagine, the GANs have been very, very influential. There is a whole zoo of GANs. There is cyclic GAN, there is this GAN and this GAN, and so on and so forth. And every day there's more of them coming, right? So they remain a very, very hot area of work.
Asif, quick question.
Yeah.
So when do the generator and discriminator will stop iterating? That is the Nash equilibrium?
Yes. So, you know, you run it after many epochs, you'll know, you look at the loss function, right? So there is a bit of mathematics. See, the minimum that the loss function can achieve, and there's a bit of mathematics, is minus log of 4. This is, you can't beat this, right? So soon what will happen is, what happens in reality is you see your loss decrease, decrease, decrease. And then after a little while, you notice that it's not decreasing anymore, you stop. Are we together? It's a standard neural network training. How do you know when to stop? You see the loss, like in the beginning, it will start like this. It will start like this and then start trailing off. When you reach a point of no returns, diminishing returns, a plateau, you stop. No point in more training.
And as if when you draw a loss curve like this, you're basically referring to either D or G.
Yeah. So what you do is very, very clever actually. In code, you do both of them together. But when you compute the loss, you compute the total loss between the cop and the thief. Right?
Okay.
So, and then see both of these losses, ultimately they'll plateau off. So you will have a very, very clever thief and you'll have a very, very clever cop. Right? And that is your generative adversarial network. It's a beautifully simple idea. It's quite interesting that you can make these two play against each other and improve, and they do actually improve, right? There's some instability in the original versions, but now people have been, to a large extent, been able to completely solve it. Now, I wouldn't say that they're completely solved it. They have been able to solve it quite a bit. But even today, you know, you take some of these GANs and you run it once, it will learn very well. You learn it you train it the next time, now things are not so good. So people often try to run it a few times and pick the best model. They freeze it. And there's a lot of work that actually creates very stable GAN training.
So Asif, one question. So I think originally when you started explaining, I thought we are trying to perfect the police by means of a thief. But in this case, looks like we are trying to perfect the thief or the generator, and police is just a guinea pig.
Absolutely. You smarten the police, but actually you don't care much about the police. You just want a very, very clever thief.
Yes. So all the applications are basically just using the smart generator, basically.
Exactly, because the generators can do, it's like free money, right? Imagine you cooked up a printing press in your backyard, or in your house, in your basement, and it could print a currency just as good as the real one. Would you think it's of value?
Yes.
So pretty much that's it. That is GAN.
That's a very clever idea.
Police will stop, I guess, when no more it can detect fake.
Yes, exactly. So what happens is that they plateau off. See, the way it works is that ultimately the cop becomes very, very good. Right? I mean, sorry, the counterfeiter becomes very, very good. And what you're feeding it is very hard to tell from the image. So you get a good cop. But see, the thing is, even though in a way you can say the thief wins in some sense, but actually the cop also wins because the cop is a super cop. Unless you are dealing with an extraordinarily smart thief, that cop will catch most of the thieves, isn't it? Anybody not such a super thief, the cop will catch. So the cop is also benefited a lot. It's become a super cop.
Does if the examples that you gave in terms of the illustrations where this kind of a concept is useful, if you were to compare those examples with where, let's say, a studio like Pixar has already taken, that is basically they're doing multiple layers and they're doing simple matrix algebra, right?
Right.
So that technology has also reached a certain stage where they can superimpose pictures on other things. They can create virtual images, like a thing like Avatar can be created, right? There are people moving inside a jungle and all that.
Absolutely. I mean, have you seen deep fakes? I remember in the class website, I put a deep fake of Obama introducing a class. Let me show that to you guys in case you missed, just to show you what beautiful things. Maybe that's a good way for us to start with this business of what GANs can do. So if you haven't seen this video, which is there in our class website, this is high time. It turns out that these days, AI is so powerful that no less than a person, as the President of the United States comes and introduces the class. So let's watch this. Hang on, before I do this, let me share the sound, share computer sound, and I'll start from the beginning.
2020, and welcome to the Deep Learning lecture series. Let's start it off today to take a quick whirlwind tour of all the exciting things that happened in 17, 18, and 19 especially, and the amazing things we're going to see in this year, in 2020. Also, as part of this series, there's going to be a few talks from some of the top people in learning in artificial intelligence. After today, of course, start at the broad, the celebrations from the Turing Award to the limitations and the debates and the exciting growth.
Okay. I'm not able to, maybe it's not this one, but there is a lovely video. I think I posted it to our class
I'll
website.
post it in the chat, the Slack.
Oh, I posted it in the Slack.
Have you seen it?
Send it back to me on Slack?
Yeah, okay.
I want you guys to see something. Oh, here it is. Yes, this is it. Thank you. So let me play this.
It got me thinking about my full-time employees and their ability to, got me thinking about my.
Okay, let me, I don't know, this must be something else.
Full-time employees and their ability to survive on $8 an hour in New York City. And foremost in all of our minds has been the loss and the grief felt by the people of Orlando. Most of us don't get our health care through the marketplace. We get it through our job or through Medicare or Medicare. And what you should know is that thanks to the Affordable Care Act, your coverage is better today than it was before. Women can get free checkups, and you can't get charged more just for being a woman. To give his employees together to pass a common, there's a bill that would boost America's very, very hard times.
Some progress, at least within the small confines of the legal community. I think it's real important.
Here we go. President Barack Obama, when you giving a speech, make sure you use a lot of pauses.
America's businesses have created 14.5 million new jobs over 75 straight months.
We're developing technology. Every technology can be used in some negative way, and so we all should work towards making sure that it's not going to happen.
Anyway, guys, so do you see how realistic that Obama's talk was?
Yeah. You had shared that video.
That is it. So that's the worry. Deep learning plus the business of creating fake. Now you have a generator. You can go creating as many fakes as you wish. Mm-hmm. And that is both the power, the fascinating power, and the tremendous risk of, or the worry of AI. You know, with this sort of, it's heralded as a major breakthrough in AI. It certainly is. But you also have to ask this question. Is it pretty much going to tear apart the fabric of society the way it is? Anyway, I'll leave you guys with that thought, and then I'll show you some examples after the break. Let's regroup at 9 o'clock.
Asif,
Yes.
you want the link to the video you had shared about the Obama teachers at MIT?
Oh, yes, yes. Why not? Why don't we see that too? Please do share it. Did you post it to would you just post it the 2020 deep learning, our deep learning Slack, please? Oh, you did. Here we go. Excellent. Let me, am I sharing the right screen? Yes, I'm sharing the right screen. Okay. Just for fun, this is a 1-minute video. Enjoy it.
This year, I figured we could do something a little bit different. And instead of me telling you how great this class is, I figured we could invite someone else from outside the class to do that instead. So let's check this out first.
Hi, everybody, and welcome to MIT 6S191, the official introductory course on deep learning taught here at MIT. Deep learning is revolutionizing so many fields, from robotics to medicine and everything in between. You'll learn the fundamentals of this field and how you can build some of these incredible algorithms. In fact, this entire speech and video are not real, and were created using deep learning and artificial intelligence. And in this class, you'll learn how. It has been an honor to speak with you today, and I hope you enjoy the course.
So I don't know, guys, at least I find this super, super exciting. And it is both the power and the scary part that is so fascinating, so powerful, and so scary, isn't it? And yet, on Sunday, you'll realize that the mathematics is almost 10 lines at most. It's very simple. If you got the idea of police and thief, you got the whole of it. We can rewrite it in a bit of algebraic or mathematical jargon, but that's about it. And now, on Wednesday, we will do labs, and you'll find that the labs are so easy. And very, very real things you will be doing in the lab on Wednesday. It is our last session, and I thought it would be a good way to end the fundamentals part, the part 1 of this workshop. And you'll walk away, I mean, I hope, suitably impressed at your own ability on what you can do with these, with generative adversarial networks. In the second half, I would like to show you some examples from the original papers, and we will then continue on to another kind of topic, which at least I would like to touch upon. It is the topic of graphs, large-scale networks. So there's a difference between the discriminative models and generative models. In the discriminative models, which you're familiar with, you, for example, ask this question, given this input, which is the likeliest output? So what is the probability of each of the labels? Or what is the probability of a given value? How much ice cream, which is the most probable amount of ice cream that will be sold? Things like that, right? Given this input. So those are discriminative models. What is the probability of a label given the data? On the other hand, generative models, they don't ask that question. They basically say, if you look at the input and output all put together, what exactly was the probability distribution? That is the underlying ground truth, right? So it is like this. So maybe I'll show the other screen. The question, where am I? Yes, see, the question that a generative model is doing is, it's trying to gradually learn these things, this probability distributions, isn't it? Once it has figured out that data is distributed in the 2 corners here, this is, in the language of mathematics, you say that you have figured out the probability distribution of X, of the data. You have figured it out. And once you have done that, now it becomes very easy. You can generate as many instances of data as you want. And That is lovely. So I'll give you a very simple example to make it real. Suppose a data is coming from a bell curve, right? So what happens is given X, you get a Y. Right? This is your Y. And it's a bell curve centered around some mu, and it has some sigma square variance. So you get data. So you can do training in two ways. You can either try to figure out some, a discriminative model that tries to capture the shape of this curve. The other thing you could do is you could basically say, y, if I take it to be, let's say that 2 pi, square root of 2 pi, up to some amplitude, and then e to the minus x minus mu square over 2 sigma square. This is the equation of a bell curve, by the way, guys. So now what you're saying is, what is mu and sigma square? And A, the amplitude. If I knew these three things, then what happens? I can generate arbitrarily many points that will look exactly like the input data. Do you get the point, guys? Huh? If you figure out the bell curve, now how many points can you generate that looks like the data, the original data? You can generate infinitely many points. Right? And therefore, what you have done is, this is your, in effect, in a very oversimplified sense, this is your generative model. Right? You have created a model which is about a joint probability of a x and y. Right? What is the relationship? On the other hand, when you make a other model like a y, probability of y given x, like for example, y is something like that, ax plus b, or you try to fit something like that, then the game is different. Right? Here, you're not trying to predict. I mean, you're in a way indirectly trying to predict y, but you're not. What you're trying to do is discover the underlying distribution which produce the data to begin with. And when you can discover the underlying distribution, now you can generate arbitrary many models. So how does it relate to images? See, what happens is that, think of a 1. So you have a text, a digit. It is, let's say, 1. It is, if you think about it, it is some pixels, right? So if you stack the columns together, it will become, I don't know, 1, 2, 3, 1, 3, then 4, 5, 6, 6, something, somewhere, there will be shading. This is your, suppose this is 28 by 28. This is, or in this particular case, 4 by 4. Let me just write it realistically. 4 by 4. When you stack the columns, 1, 2, 3, 4, vertically, when you stack it, you will have 16 is equal to 4 by 4 vector, feature vector. Right? And now what happens is, you take all the ones, and you would all agree that most of the ones, they will look like minor perturbations of this, maybe somewhere here, something like that. So what happens is, all of these ones in the feature space, in an abstract feature space, they will occupy a region. This region is in some sense 1. This region is in some sense 2. Are we together? Right? And the game that the generators play is, they figure out of which part of the feature space is valid data, legitimate data, and which part of the feature space not to go near and not to generate points there. Are you getting that? Are you getting that, Pradeep? Right? So what you're basically saying, if you go back to this example, is that this green point, don't generate this green point. A point here is good.
In a way, it is basically finding the real Y, like which has generated the data itself.
Yeah, what you're looking for is a joint probability distribution, input and output, the complete distribution function, right? It has figured it out.
So in the regular problems, can we use GAN to just find out what is the distribution itself? Because many times that's the problem.
Not just GAN. See, the trouble is, GANs don't tell you the distribution. That is another problem. See, so let me answer your question. What happens is, real life is very complicated, right? So this probability distribution function, right, is very hard to figure out. It is highly nonlinear, highly hard to multidimensional, and not terribly practically useful. So can you figure this out? And if you really tried to do something, there are ways that you could sort of see what the GAN is seeing. Therefore, you can get an idea of what this function is. And we'll talk about interpretability of the model. You know, I said explainability and interpretability of the model in the way, in the part two, that will be one of our starting points. So yes, you can, but you know, when you GAN or these generative models, like for example, there are many of these. This is one: negative sampling, inverse transform, then Markov chain Monte Carlo. Right? They belong to a family of algorithms which are generative, and the beautiful thing is that they can generate a lot of new samples representative of the original data without necessarily needing to write the probability function in explicit form ever.
I see.
That's the point.
And so, sir, what is the limit of this? In the original example, like one of the example, we said that that there is girl in this room and playing piano, and then picture was drawn. So, like that way, if somebody says, I need a program like say React.js or any framework, I need a program to be written doing this and this, right? So will it do this also, or in the current
the training data? See, what happens is that there are so many competing technologies these days. Remember, I talked about transformer last week.
Right.
And I showed you that transformers, some of these big transformer models like GPT-3, they're literally writing code for you. Yeah. So that is one avenue to train. Here, what happens is, can you train a GAN and frameworks like this to do some things like that? Yes, you can, but mileage varies. Right? At this moment, in writing code, because it's more a natural, see, the output is text. Whenever the output is text, generally transformers do better. Whenever the output is image, you'll notice that the GANs do better.
Okay. That's what I wanted to know, like in which area it is stronger. But it can do text also. It's just that transformer happen to be better so far.
Yeah. So these things are very powerful, and they're, see, the concept of GAN is there. Now, how do you implement it? Do you implement it using convolutions? You implement it using what? Right? And there's a very interesting thing. I was just having a conversation with one of our participants here, Chanda, right? In this a few months ago, his son did a very interesting paper, which was to train machines, the textile machines, to work with the kind of cotton seeds that are there in India, the kind of not so long length, short length cotton that is produced by Indian farmers. As you know, long cotton is very, very good. Apparently, there are a lot of machines in the Western world. Everybody has perfected the technology to deal with it. But as those seeds come to India and they are all under copyrights and whatnot, then patent and whatnot. So what happens is that the Indian farmers were losing out. So Chandra's brother here is an idealistic person. He does grassroots innovations. Amongst the innovations that he has done is that he wanted to create a machine that can deal with that. And he has created the machine, the textile machine. Trouble is to calibrate it is, you need another machine which is extremely expensive, right? To calibrate it properly and fine tune it. So the question that Chandra's son here did is, can you instead create a neural network that you can use instead of using instead of going and renting this machine, which will cost you tens of thousands of dollars a day, which is hard to afford. And sure enough, he succeeded at doing that, and he's writing a paper on that. Okay? And I must say that Support Vectors was involved in helping him out.
That's great.
Yeah, I can share the reference at some point. If probably I'll put it in Slack. He has put it as an archive paper.
Yes.
Thanks, Asif.
Yeah. So this is a great work. And by the way, he's just in college. He has not even finished college. Right? So this is the power of this. And if you look at the architecture of what he has done, it is in effect a GAN. Right? There are two sides which are
actually neither he nor I knew it was GAN, but now that Asif is giving the lecture on GAN, we realize that it is very similar. I mean, we had a very similar cost function where there was a original one RNN was trying to simulate the data, which the second RNN will think that it is actually the real data. So it was, in some sense, it is very parallel to this GAN framework where you have a generator and an adversary.
Right. So nice guys. So I'd like to just show you a couple of things in the interest of finishing off this discussion before I go on to networks. By the way, guys, I hope you realize that GAN is a topic on the course website. If you are seeing, maybe I should go there and remind you that, I don't know, how many of you visit the websites? Do you guys visit the course portal or check out what things there are? It is filled with a lot of things, guys. For example, the interview and job offer tips. There are all sorts of tricks with pandas and glossary of terms and interview tricks, you know, what to do, so on and so forth. Many things are there. So amongst the things that are there is the GAN. So this is the original paper. By the way, there is one explanation which I found to be with just a little bit of mathematical knowledge, you'll completely enjoy. It is by this person, Ali Godse. Ali Godse makes is a little bit slow, and in the old traditional style, he'll write on the blackboard, whiteboard. And some of you who have actually visited support vectors will realize that I also fall in the old school, but he's really very good. You can listen to his YouTube video on GAN, and it's just wonderful. I have put it here, and maybe it's not visible on your screen, so I'll make it bigger. So this is the paper. This is the video. I'm saying, guys, that if you want to, usually what happens is you want to learn things from the textbook. But I feel that this paper, the original paper, is a masterpiece of clarity. If you just read the paper, and you can skip the mathematics in it, it is the best introduction to GAN itself. And then watch the video of Ali Godse. That is all you need to do. Forget your books, forget your practical books and labs and all of that. Just go and watch these two things. And after that, in the practical, of course, we'll do the lab, we'll do the PyTorch code and so forth. So these are the two good resources. I'll go to the paper for a moment. So this is the paper, he goes on talking and so forth. So the basic idea is that, once again, I've used the same notation as this paper. D is for the police. G is for the generator, right? Discriminator and the generator. Now, those of you with that sort of a minimax background, this is a standard two-player minimax game. Is the loss function. The discriminator tries to maximize the ability to tell the things apart, and the generator, the thief, tries to make sure that the difference between the fake and the real is as small as possible. That's why it's called the minimax, the adversarial, right? And the basic idea is that, see, what happens is that in the beginning, if you look at these black dots, let's say that is your real data. And in the beginning, the generator always has some hypothesis about the real world. Let's say that the initial hypothesis of the thief is, it is producing data from its own internal distribution that it has in mind, like this, like the green line, right? So what happens is gradually, step by step, do you see that the green is getting closer and closer to the data point? And finally, the green is now sitting upon the data point. It sort of have figured out the distribution that will produce this data, isn't it? And notice that I'm not saying that find the best fit curve or something like that. I'm instead using the word distribution, or the probability distribution, because that's what you use. What is the distribution that will align this generator to produce data that is real data, right? So that it could essentially be a source of fake data that nobody can tell apart, right? So that is the gist of it. And as I said, there are two steps to it. One step, you update the discriminator, means the police. The second step, you update the thief. Do you see this? There's a little bit of mathematics which you can ignore unless you're interested in it. And on Monday, we'll talk about it. So the mathematics guys just purely ignore it. Huh? This uses the sort of a Jensen-Shannon divergence, for those of you coming from information theoretic background, which is a symmetric KL, KL divergence. Ignore all of that. And you don't need to read any of the mathematics. The explanation in the beginning, the way he talks about it in the first page, just up to here, just two paragraphs, puts the gist of GAN in your mind. The rest of it is just, in fact, you can look at this picture, and most of the paper, unless you're interested in the mathematics, you can just skip. Then let's go to the results. Right? So here, these are the results, and I'll just increase the screen size even more. Are you guys seeing my screen? So you see the ones in yellow, right? That is real data. So that is the real data. And the one just next to it, to the left of it, do you see this 9028 where my mouse is? Right? This is the data randomly generated by the generator, by the thief. And so all the data here, except the ones marked in yellow boxes, they are real data. And do you see how the last column, these two columns are very closely matched, how legitimate it looks. Do you agree, guys?
Oh, yeah.
Yeah.
Yes.
Look at this, another example. These are some of the instances that were fed. And now look at these generated instances. Would you agree and look at these faces and say, my God, they look like photographs. They look like pictures.
Scary ones, but yeah.
Yes, and the thing is, this was the original paper in 2014. Today, the state of the art has moved much, much further. It is not so blurry anymore. It's much more 3D, much more color, much more realistic these days, right? So it generates very realistic pictures. And here, so things like that, you can see it gets pretty close. And so, and this was the original. It started a whole body of work. Now, if you go back to the course again, where am I? DC GAN. I think I should mention the results from DC GAN also. GAN paper. I'll add it to the course website. DC GAN. This is the original paper of DC GAN.
The Wikipedia, the GAN Wikipedia has a picture which is looks very real, the generator of the GAN.
Oh, okay, nice. Let's go look at it together. So this is the DC GAN paper. And this also, by the way, so the state of the art has moved very, very forward. So this is do you notice that the generator is a convolutional network run backwards? Typically, you have a big image on the left. And gradually, as you move forward, you get a smaller and smaller image and a lot of channels. But you start the opposite way here. You take 100-dimensional random data, or people take either random or they take Gaussian normal distribution, and they just feed in. And right away, what did it do? It created a 4x4 and 1,024 of those features, right? So it projected it into a large dimensional space and created 4x4 images of all sorts. And then it is just doing the reverse of the forward pass. It's just going the other way around, expanding it out. Right. The only thing is max pooling has been taken out. There are minor things. You use leaky ReLU, this, that, but let's not get caught up in the details. Yeah. So now it has created these images. When the generator now, you ask it to produce images of bedrooms, and it comes up with all these images. I don't know about you guys, but this looks to me a pretty realistic images of, on the first pass, it produced this. After a little while, it begins to produce this. And these are all things, photographs, that just didn't exist. The GAN is just conjuring it up out of thin air. Isn't it impressive?
Yes.
Yeah.
And they look such photorealistic, like they literally look like photographs. And the state of the art has moved even further. And the amazing thing that you'll realize on Wednesdays is just a few lines of code. That's the power of deep neural networks, right? And of other things and what features it is saying. Anyway, this goes into this, that it is trying to understand what the features are. How is it understanding bedrooms and so forth? We'll leave that. I won't get into that. But here's the thing that I was talking about. You take a smiling woman and you subtract a neutral woman and you add a neutral man, and all of a sudden you have a smiling man. Do you see? You have lots of generated pictures of a smiling man. You give it a few. Yes, go ahead, Patrick.
What is the corpus here to be able to detect this? Is it the features that like from your filters that it updates?
Yeah. What happens is that when these GANs are trained, at the end of it, those filters get trained. Those filters get trained to either generate or detect specific features, right? Each of the filter is a detector of a specific feature. One will detect, remember, edges, circles, this, that. So at the end of the day, they become pretty smart at either detecting or generating features. So when you give it images like this, it knows which part of the feature space you are. Then you give it vectors like this. So in other words, just vector thing. Smiling woman will occupy one place in the vector space, embedding latent factors. Then you subtract a neutral woman. So what do you get? You'll get the ghost of a smile. Right? What you're left with is just some other vector, which is sort of abstract. In the feature space, of course, it's a real vector. Not the feature space, in the latent space, in the embedding space, it's a real vector, except that it doesn't have any real meaning. It's like a smile without a person. And then you add a neutral person there, and then this vector and this person added, you go to another region of the embedding space, and that, if you go and see, if you draw from that region of the embedding space, and you reshape that, that point into a 28 by 28 image, let us say, or whatever, square it into an image, wrap it around, reshape it into the image, that column vector, make it two-dimensional, and suddenly it will begin to look like a smiling person. Smiling man. Do you get the idea?
Yes, sir.
That's it, isn't it? I mean, I don't know if you're excited. The first time you encounter, you just say amazing, isn't it? Even after all this time, I still feel amazed. Every time I open these things, I feel amazed. Likewise, here is a guy with glass. You subtract the man out of it, and you have just the wearing of glass hanging, a vector that represents just the wearing of a glass without necessarily a person, a ghost with a glass. Then you add a woman, and the ghost is gone. You have the woman wearing a glass, and quite realistic. It almost looks like, even in this early versions, and by the way, state of the art has moved much further ahead. This looks to me a fairly reasonable job at creating the picture of a woman wearing glasses. Many women generating lots of pictures of women wearing glasses. Would you agree?
Yes.
So that is what it is. That's what GANs are, guys. Huh? And you can do. How do you convert this to this? There's a process of going from here to here and so on and so forth. I'll let you have fun, and that finishes the topic of GANs. Now what I would like to do is, again, I must say that I did not explain the mathematics deliberately, because I decided that we get into more technical depth on Sunday. So I will spare people on today to that. But if you want, obviously the video recordings will be there. And let me now go and review what we have learned. After we review, I would like to take some time to introduce you, if possible, to the new world of graph neural networks and so forth. But for now, so what did we learn? We learned that we need to get a smart thief, because the thief will create a lot of fake money for us, isn't it? That fake money being whatever, counterfeit money being counterfeit images, counterfeit this, that, whatever, pick your thing. But we'll start with money, dollar bills, $100 bills, $1,000 bills, and so forth. So the generator is the thief. The discriminator is the cop. Now the thief will try to, his goal is to fool the cop. And the goal of the cop is to not be fooled. They have adversarial relationship, right? And so the way you train them, and the cop is essentially a classifier, binary classifier, says fake, not fake, right? The way you train it is first you give the cop the chance to learn. Whenever you train the cop one step, you give it half and half of fake and real data, and you honestly label it. The fakes you label as fake, the real ones you label as real. Let the cop predict, then the cop will make mistakes. You get the loss function, you back propagate, and you have a smarter cop, slightly smarter cop. Next stage, you make obviously the thief is now falling behind. So now what you do is you make the thief generate some images, but then you misinform the cop, as the thief will do. It will try to pawn it off as genuine. So even though it's fake data, you label it as though it's real data. You label it as real and you give it to the cop. Now the cop will get confused because, you know, here it is, it's saying one real data, but actually its model, if it is any good, will come up with somewhat lower probabilities, and then it will lead to loss. So suppose the cop is pretty good at it, and then the thief is lousy. Then what will happen? There'll be a big loss, right? The gap between y and y hat will be big. Let me say this point more. So let us say that the cop is pretty good. The generator this fake generator has produced data, then what will happen? The fake will claim 1. Police will say, no, I'm not going to get fooled. I'm claiming 0.1. Means there is a significant amount of loss, right? Likewise, another image, it will claim 1. And the police will say, no, I believe it's just less than 1% chance is genuine, right? So now the loss is even more, 0.0, like 0.99, I don't know, something like that, right? Something here it is 0.9. So things like that. So a lot of big losses will be there. From the big losses now, the generator gets the gradient descent, right? It learns from the backprop and gradient descent. So now the generator will generate better fake images. And so you repeat this cycle. First part, you make the cop a little bit smarter. In the second part, you make the thief a little bit smarter. Cop smarter, thief smarter. And this is the minimax, because they have, one tries to maximize, one tries to minimize. And so end result is that, right, the cop will try to amplify the difference between the two and be able to figure it out. And the thief will try to minimize the gap between a real rupee, a real dollar and a fake dollar, right? And see, notice the fact that the thief never sees the real dollar in its life, right? The thief is just generating out of, it's just cooking up. But it is listening to the chatter in the police station, essentially. In other words, that's a poetic way of saying that it lets the backprop flow from the police to it, backprop of gradient. So the gradient flow, it sort of listens to and learns from that and gets smarter at that. And those are the 2 steps of generative adversarial networks. With that, we are guaranteed to reach a stable point, reach a minima. The trouble with the minima is it's not always there. It will reach a minima. So for example, one of the problems with the initial GANs was that, let's say that you have 10 digits, 0 to 9. First, let's say that the thief produces a 0 or maybe 3, and then the police tries to learn about 3. Then police gets better and better at detecting 3. And the generator, what happens is that the neural network generator shapes to produce better 3, and it's not producing other digits. And soon it becomes very good at producing 3s, right? But then the cop catches up. And now it figures out some way to tell the 3s. So then suddenly, because you're feeding in random numbers, the generator generates something that is not like a 3. And all of a sudden, the cop is completely fooled, because all that the cop knows is how to detect a 3. And the whole cat and mouse game starts all over again. And this time they gravitate towards 4, or they gravitate towards 7. And so they can endlessly be getting trapped in local regions, sort of states of equilibrium. And the game may never stop. The algorithm may never converge. It will just keep going round in cycles. It will get stuck here, spend some time, then suddenly jump here, spend time, and suddenly jump here, spend time. And it may keep on going that. So people have come up with ways to improve upon it. And it's not completely solved problem, but it's much improved. So if you look at the DC GAN, it's a little bit more stable. One of the nice qualities of DC GAN is the generator is actually, in some sense, a convolutional neural networks run backwards, right? Or architected backwards. And the detector, discriminator, is of course a standard coordinate with a classifier at the end, a softmax in the end. And so that it is, they play. One of the advantages of that is you get this property of, yeah. So here's the thing. The way to understand it is, suppose you have a duck and a cow. Right? What happens is that, suppose this is the data distribution in one dimension. You could be here or here. The duck looks like this, cow looks like this. If you point at these red dots are the point sample from that. But the generator in the beginning is just creating absolutely uniform distributions. But after some time, what happens is that it learns to produce data only in this region. It picks up the distribution. That is generative learning. Right? That's all it is. And now you can generalize it to higher dimension, this generative business. One analogy I gave is a bell curve, right? If you want to learn a bell curve, you can just figure out the mu sigma square, then you can generate arbitrarily many points similar to the original distribution. Right? And so it has a very good vector arithmetic associated with it. You can actually take, just as word embedding says a queen is equal to king minus man plus woman, you can play the same game, and you just saw us do that. Right? We saw the man with glasses minus man plus woman becomes a woman wearing glasses. Right? Then also gated GANs produce neural style transfers. Right? You can take a picture and paint it any way you want. Yeah. Impose the style of a great artist upon your fairly average picture, when suddenly it will turn out that Rembrandt has come out of his grave and started painting a beautiful picture of your children. Right? So that's the thing about these things. You can do with, so long as the output is images, these GANs do really well. You could give it inputs. You can say, here's the thing, give me a room with a window and a girl playing piano. And it can then start producing images like that. Right? One of the questions is, when does it converge? Well, quite simply, because you can look at the loss function over time, over iterations of both the generator and the discriminator. You can see at what point to stop. Right? That is it. And what it is doing is, it is just learning the probability distributions. I gave this example in 2 dimension of a cow. Let's say, yeah, let us say that in the feature space of weight and size, so from 1 dimension I go to cow, ducks are light and small, cows are big and heavy, and any points in between are basically very easily fake data, right? So the cop will notice it. So soon the generator learns to produce points in only these 2 corners. So suppose a green in the beginning, these green points are what the generator is producing. It is all over the place, very easy to get caught. Gradually, it starts producing points only in these 2 corners. And when it does that, what it is doing is it's producing very realistic pictures of cows and ducks. Right? And that is generative adversarial network. Guys, I noticed that it is 9:43. I was thinking maybe I'll introduce the concept of graph neural networks, but I think may not be a very good idea. It might be information overload. Do you guys want to hang in here till 11:30, or should we call it a day? I should review it and call it a day today. We have 15 minutes.
We can
call it a day. Huh? Okay, guys.
No, we can wait. Like,
I think we can call it a day. We have.
Okay, getting tired. Huh? Okay, guys. So then today was the last theory session of part 1, guys. I will just review what we covered in this course. I don't know, if you look at what we covered in this course, you'll realize that we covered between all of the sessions that we did. Already, I'm just now going to share our course website. let's see. So please, just for your information, guys, be aware that all the videos are there. Do you notice how many videos are here? And this still does not include the recordings from Sunday, which will come hopefully tonight, the one on bird. We have a lot of recordings actually, 1, 2, 3,
27.
27, yeah, and 28, and including today, it will be 29. By the time we finish Wednesday, it will be 30. And then we'll have our quiz review sessions whenever we do. And then we'll have our Sunday when we go into the mathematics of GAN. The original research paper of GAN is a reading. So we have covered a lot of material, and this session list says it all. We talked about deep learning, what it is about. We learned about transfer learning. So let us ask ourselves, do we know what transfer learning is, guys?
Yes.
What would be a good example of transfer learning?
BERT.
BERT, yes. We use BERT, we understand that. We created a first neural network using PyTorch. We did all our labs in PyTorch. Once you understand the theory, these libraries begin to look very simple. You have the forward pass, the loss function computation, the backward pass, and then the back propagation of the gradient, and then finally the step in which you update the weights, gradient descent step. Literally 4 steps, and in PyTorch is literally 4 lines of code. If you look at the labs and go back to the code that I wrote, the main loop, you remember that it was actually 4 lines, effectively 4 core lines. That's the inner loop of the learning in machine learning, right? The word learning. We did that. We did quite a few of the quizzes. Every week we had a quiz or more quizzes. Quiz 0 was to review what your background. Quiz 1 was basically on transfer learning and on interpretability of models and all the things that we'll cover. We did not do a lot of model interpretability and explainability. That is for part 2 and 3. Right? We didn't have the time to do that. We'll continue on. We did a bit of Python. For those of you who didn't have Python background, go and please review those videos. There were help sessions I gave for the lab. Then we talked about the fact that why are neural networks so powerful? By now, today, we are in the 6th week and ending the fundamentals. I hope if I've convinced you of anything, I've convinced you of the awesome and fascinating power of neural networks. And of course, it's dangerous too. Right? It's an amazingly powerful tool, right? And one of the basic questions that comes is, why does it work? So in that framework, we talked about the universal approximator theorem, right? With respect to neural nets. We talk about the fact that a single layered neural net can approximate any function that you want, right? It's pretty clever at it. We saw that in the lab examples. We created all sorts of functions, and we could see that the neural net was able to get to it. Then we built our first neural nets. We did quizzes on universal approximators. We did all sorts of things, deep neural nets, and then we talked about Ola's blog that explained what does it do? If you think from an abstract perspective, the input space and the output space, why is it that you are able to capture nonlinear decision boundaries, relationships? And when do you know how many nodes you will need in your layers? That's a lovely Ola's blog, very nice. Then we went on to do regularization methods, lots of them, L1, L2, dropout, early stop, right? And normalizations, batch normalizations, and so forth. And all sorts of regularization methods. They are at the heart of deep learning. The reason we can do deep learning so successfully today is because of that, right? We can create really deep neural networks, residuals, short circuits, and so forth. And that's what makes it possible to make, these days you create neural networks that is 1,000 layers deep. Right? So that is it. We learned the concept of backpropagation. We learned about activation functions, right? And then we did all sorts of quizzes and labs on them. Then we did the visualization of the loss landscape. I showed you what is the effect that regularization has, or different things have, batch normalization and other things have, on the loss landscape, right? We saw it as the examples and pictures. That one, at least I find very useful in understanding what is wrong or what is right with the models you're building. I'm surprised that not many textbooks or people talk about it, but it's a very, very useful tool to know whether you're getting lost or you're converging to a good solution. That is that. The problem of vanishing and exploiting gradients and what batch normalization does. We talked about convolutional neural networks, which are this business of filters. And then we did about, we did this lovely paper which uses a transformer for object detection, which I hope you guys liked it. Then we did this vector space representation of text, TF-IDF, and so on and so forth, and word embeddings. In particular, we went into the detail of word2vec quite a bit. One particular implementation, scriptgram, we did end-to-end implementation nodes. And then finally, we went more into transformers. Actually, we did the transformer lab before I gave the transformer theory. And then we had the understanding of recurrent neural networks and transformers. Okay? RNNs and LSTMs and GIUs and transformers. And now we did today one big architecture, namely generative adversarial networks. So this is the fundamentals, guys. This course, I focus fundamentals a lot more in making sure we understand all the concepts so that going forward, we focus a lot on actual doing things. We want to code, we want to build something, we want to get a flavor of what does it mean to do that. And one of the most pleasant surprises will be that once you become fluent with the concepts and with PyTorch, first of all, new research papers that come are easy to read. If you have never read research papers in this area of deep neural networks, of course you haven't. I hope we have read a few papers in the last few weeks. I hope you must be feeling that the papers are not as hard to understand, right? We are not talking of some deep superstring theory paper. We're talking about very straightforward field. Yeah. Great breakthroughs, but easy to understand. And so one of the things we'll do in the part 2, part 3 is we'll take the breakthroughs as they come. We will read the paper and we'll translate it into code. Are we together? Like, for example, this object detection data, we will literally take the paper and we'll implement the entire thing in code ourselves. And then we will take scenes, pictures, roads, pictures of the road and this and that, and we'll see how well can we detect things in that. Object detection we can do with that paper in that. Right? And so we'll become much more fluent with the practice of deep neural networks. That, in a sense, has been a theory, guys. And in the next, in the lab, we'll finish that. Guys, 2 requests. I'll send you a course survey. Please do fill the survey. Also, do keep taking your quizzes. It's important because that's how you will know whether you know or not. And don't expect to get very good marks in the first attempt. Whatever you get, take that as a baseline. Go read again, review again, watch the videos again, and then come back and take the quiz again. And keep following the topics in your textbook. The main textbook. It's very straight. How many of you are finding the textbook now relatively easier to read after the sessions? Anyone? Anybody has a feedback?
Yeah, it is more easier to read now.
Much easier to read. Yeah. So guys, if you are stuck, reach out to me, right? Or reach out to people here. I would love to sit and explain again because I want to make sure that your foundations are solid so that when we go into the practice of things, it is a smooth sailing there. There your worry should be, why is my code not compiling? What is the bug here? This, that. You should not have worries about, I don't understand anything that's written in the code. Right? It should be more like, I know the general flow of code, but what do I do to make it work? Or how do I make it work better? And things like that. Right? Can I use it to solve this problem? We'll completely change our mentality in the next parts of our workshop.